Okay, good morning, good afternoon, good evening, everybody. Can somebody quickly confirm that you can hear me? By maybe raising your hand in the... Okay, I got a raised hand. Thank you. Yeah, fine, I can see that. Thank you very much. So Happy New Year and welcome to the first Eminar of 2021. I'll quickly switch on my video to minimize the surprise because, as some of you may notice, I'm not Alan Jones. Alan is having a sort of examination today. He might be listening, but he cannot host it today, so I'm taking over for Alan today with the first Eminar for 2021. I assume that most of you have used Zoom or participated in one of those meetings because I do not have Alan's explanatory slides, unfortunately, but the most important things for you to know are the question and answers feature, which you find the button as part of the panel of your Zoom at the bottom. And so if you have any questions, because you will not be able to talk, then please type your questions in there and it will then appear. I will see this and I will alert Alan Chave, the speaker for today, if there's something in the middle of the talk, or otherwise we'll deal with those questions at the end of the talk. So yeah, today we have Alan Chave from Seoul Oceanographic Institution as a speaker, and he's going to talk to us about multitaper spectral analysis. I think if you're in the EM community and you have dealt with MT processing or EM processing in any way, you will have heard Alan's name. And in a way, it also follows on from the fundamentals of time series processing talk that Xavi Garcia gave before Christmas in early December. And before we start, just very briefly to remind you of the next talks that are coming up. So next week on the 13th, we have Joel Jensen from Anglo American talking about natural source EM methods for mineral exploration. And then the week after that, we have Paul Bedrosian from the USGS talking about the US Array MT program. And in 3 weeks, I'm going that far because it's also applicable to, or related to this talk. We have Pierre, okay, I'm not going to pronounce this name properly, okay, sorry, from BRGM talking about Razorback, an open source Python library for robust processing of magnetotelluric data. So I will assume that some of the topics that Alan will touch upon today are relevant for that talk as well. And so now I'm going to hand over to Alan, who I should mention too that I have muted him before, so you should unmute yourself, otherwise we won't be able to hear you. So please go ahead, Alan. You're still muted.
Yeah, I just unmuted it.
Okay.
So this talk is going to be at a somewhat more fundamental level than what Chave did a few weeks ago. It's not specific to any particular application, but rather it's a general way of approaching spectral analysis. There are fundamental conflicts involved in any spectral estimator. The desired properties of a spectral estimator that you can't actually achieve at the same time are, first of all, that it should be low bias. When I say bias, what I really mean is leakage from low power parts of a spectrum into the, high power points of the spectrum into the low power points, thereby obscuring features. It should also be consistent. The statistician would say this means that the estimator converges in probability to the population value, but a more simple way of saying this is that as the number of data rises, the precision of the estimator gets smaller and smaller. It should be efficient. Loosely speaking, this simply means that you're using all of the data or as much of the data as possible. Again, the statistician would say that it achieves the Kroner-Rao lower bound, which is a bound on how small the uncertainty on any estimator can be. You can't beat this one. It should be statistically characterizable. That's certainly true of what I'm going to be talking about today. There are estimators out there that are not statistically characterizable, notably the Hilbert-Huang transform. And they should be robust so that if you have a few bad data, it doesn't completely bugger up your estimate. There is no method, including the one I'm talking about, that can simultaneously achieve all of these goals. Taking a high-level view, there are two classes of spectral estimator. The first of these are parametric. They're based on a time series model. These are things like autoregressive, maximum entropy, moving average. When I was a graduate student in the late 70s, you couldn't pick up a copy of JGR without reading about how super resolution of maximum entropy, a quarter of a cycle of a sinusoid, you can get a spectrum out of it. It's all nonsense, of course. The problem here is that you have no a priori way of knowing what time series model is the appropriate model, and you can get wildly wrong answers if you don't have that correct. Then there are non-parametric estimators. These are based on the Fourier transform. The earliest ones of these were the indirect estimates, which were based on the autocovariance sequence, and later the direct estimates, of which the multitaper estimator is certainly one. The indirect estimator, you compute the traditional way of doing this is you first compute the autocovariance sequence in the time domain. You multiply this by a lag window. You compute the Fourier transform, and you get the power spectrum. This was the Blackman-Tukey method of the early 1950s, when taking a Fourier transform was actually fairly time-consuming. That when the fast Fourier transform was rediscovered, this certainly went out of favor. But there are other reasons for it not to be in favor. That estimator is in fact equivalent to an extended periodogram, where you take an endpoint time series and extend it with n+1 zeros, take the Fourier transform and square the coefficients. That indirect estimator, the periodogram estimator, is the lag window convolved with sine 2 pi f over 2 pi f, which is the Fourier transform of the default window, which is just a square. That it's one everywhere and where there's data. The problem here is this is badly biased because this default window has terrible side lobes. This estimator is obsolete and should never be used. And I have an example here. This is an example taken from a paper by Thomson and Haley. It's 1,000 samples of barometric pressure with a sample interval of 10 seconds. It's taken, I believe, from Black Forest Observatory, the IRIS site. The blue is the periodogram, and the black is a smooth version of the periodogram. The red is a multitaper estimate with a time bandwidth of 8. The difference at the highest frequencies between these two is about 8 orders of magnitude. And you're at the quantization noise level at those highest frequencies. The periodogram is completely useless at virtually all frequencies. It's dominated by bias. This is not an unusual data set. It's simply 24-bit data, the kind of modern day data that we all have. And it shows you, I think, succinctly why this is a terrible estimator. The direct estimate, the earliest one of these was the band averaged estimate, where you take a data taper D, choose your favorite, there are hundreds of them out there. You effectively convolve that with the Fourier transform of the data. You smooth it with a convolutional smoother W. And this has serious problems as well. It's obsolete and should not be used. The problem here is that there's no optimal choice of D, at least in the band average literature. There's not, and the smoothing is arbitrary, and you can easily smooth things away that you would like to see. And then finally, there's the Welch overlap section averaging method. This is where you take a long time series and you divide it into short overlap sections. You window each section, Fourier transform, and then take the average or a robust average of these. All of the robust estimators that are in use in magnetotellurics use this general approach. This is an excellent approach when the frequency of interest is not of order 1 over the length of the data set. Unfortunately, in lots of geophysics, that's not the case. In fact, the Percival and Walden, which is the classic textbook on spectral analysis, recently came out with a new edition. Just came out at the end of last year. No, at the end of 19, I think it was. Anyway, one of the themes that goes through that book is that there are really only 2 ways to do spectra. One is this WOSA method, the other is multitaper, and the others are obsolete. So the summary here is that parametric methods require information that you don't usually have. Indirect methods are obsolete. Band average direct methods are obsolete. WOSA is a good choice when the frequency of interest is not of order 1 over the time series length. So it takes us to the multitaper method. This was originally proposed by David Thomson of Bell Labs in 1982. I think Dave may be on this call. I did invite him. It has the advantages that it is a small sample theory with sample size explicit in the estimator. Its bias is quantifiable and controllable. It is consistent without ad hoc smoothing. So it does get better as the number of data go up. The resolution is well defined. In fact, it's a free parameter that you, the analyst, gets to choose. It has high variance efficiency. It is data adaptive, or it can be data adaptive. I'll talk about that in a minute. And finally, you can at the same time evaluate stochastic components, if you like, the continuous part of the spectrum, and line components, the deterministic part of a spectrum. They can coexist and they can be analyzed at the same time. No other method has these features. I'll start with the Fourier transform pair. If you go into a lot of textbooks, particularly those written by double E's, the inverse Fourier transform is a discrete transform. That's not really correct. The Fourier transform is in fact entire. It's an analytic function of complex frequency anywhere in the complex plane. It's not just defined at intervals of k over n. That is a computational convenience, but not a theoretical need. So I'm going to use this Fourier transform pair where the transform from the frequency domain into the time domain is an integral over -1/2 and 1/2, and I'm assuming that the data are sampled at intervals of 1. So the -1/2 to 1/2 is the Nyquist interval. You could also, if you prefer, multiply the 2 by a delta t and put it in dimensional units, but it's not really needed. And the transform into the frequency domain is discrete. The form I've shown here has time centered at the middle of the interval. This is there for mathematical convenience. It doesn't really matter. It's just a phase factor and can be ignored. We then go to the Kramer representation. It is well known in statistics that a time sequence that is generated by the superposition of random infinitesimal harmonic oscillators, this is called a harmonizable process, has the spectral representation. X sub n, the time domain version, is this integral over the fundamental interval -1/2 of the Fourier variable e to the I2 pi f times an increments process dz of f. You can't actually compute dz of f. You can compute its moments. So its expected value is the amplitude of any line components mu sub I at the frequencies where those line components exist. The expected value of the absolute square of dz of f is s of f, the power spectrum, times df. And the expected value of dz of f and f prime, where those are distinct frequencies, is 0 for a stationary process that breaks down for a non-stationary process. I'll talk about that at the end. So if you look at this, and you take the definition of the Fourier transform from the previous slide and plug it in there, you end up with the fundamental equation of spectral analysis. So you have a the Fourier transform x of f, you have this orthogonal increments process dz of nu, and you have a kernel in the middle there, which is called the Dirichlet kernel, sine n pi f over sine pi f. Spectral analysis is then estimation of the expected value of absolute value of dz squared, and harmonic analysis is estimation of the expected value of dz. This is an integral equation of the first kind. You also could view this as an inverse problem where the known is the Fourier transform x of f. The unknown that you would like to know is dz of nu, and there is a bit of physics that goes into determining how those two are related, and that's the Dirichlet kernel. In fact, you can solve this problem as an inverse problem. I'll treat it as an integral equation of the first kind, which fundamentally is almost the same thing. So there's a well-known theory of these integral equations of the first kind. They do not have exact solutions. You have to find approximate solutions. Obviously, this is very analogous to an inverse problem where dz of nu might, for example, be the electrical conductivity of Earth, and x of f might be the empty response. And the Dirichlet kernel is the physics that relates the two of those. If we think about a generic integral equation, not the one I'm dealing with there, where the known is y of x, the unknown is z of x, there's a kernel function in the middle k, which is symmetric, which the Dirichlet kernel certainly is. The way you would solve one of these is to first find the eigenfunctions of the kernel function. These are the psi k and the eigenvalues, the lambdas. And then you can solve the problem by projecting the y onto the eigenfunctions and expanding in terms of the eigenfunctions, as in the second to the last equation. The problem here is that the eigenvalues lambda sub k, which you're inverting, of course, go to 0 as k goes to n. And so it becomes unstable. You have to find approximate solutions. The simple solution is to truncate the sum at some point. There are fancier ways of doing it as well. Again, just like an inverse problem. Well, for the Dirichlet kernel that we're dealing with in spectral analysis, the eigenfunctions are the Slepian functions, or the discrete prolate spheroidal wave functions. David Slepian is one of the persons who wrote about these functions starting in the 60s and culminating in a paper in 1978. These are absolutely fundamental. If you were trying to build a laser that has the most collinear beam that you can possibly get, this is the function you would use. Your cellular phone uses these Slepian functions. So they're doubly orthogonal. The Slepian functions in the frequency domain are these u sub k's with the eigenvalue of lambda sub k. They depend on the length of the data set and a frequency, a free parameter w. You get to choose that. They're doubly orthogonal. They're orthonormal on minus a half, the Nyquist band, and they are orthogonal with a weight factor lambda sub k on this band minus ww. Lambda sub k is then the fraction of energy that is concentrated within minus w and w. And as I said, they're orthogonal and orthonormal depending on which support you're talking about. So W, or the product of n and w, which is the time bandwidth, is a free parameter that defines the inner domain minus ww. You get to choose this. The eigenvalues are real, distinct, and finite in number. They're bounded by 1 and 0. The first two nw eigenvalues are nearly 1, and then they decay exponentially to 0, which ought to give you some hint as to where one ought to truncate this sum in the solution to a first kind integral equation. And as I said, the eigenvalues give the fractional energy concentration in minus ww of the corresponding Slepian function. These are, of all possible functions, the optimal function in terms of concentrating energy concentration in a given bandwidth for a finite length time series. You can't do better than these. If you take the Fourier transform of the Slepian functions, you get the Slepian sequences. These are the time domain equivalent of it. These are, in fact, what we're going to use as tapers in the multi-taper estimate. These are actually fairly easy to solve numerically. Slepian in 1978 gave a tridiagonal analog for the Slepian sequences. So it's a tridiagonal eigenvalue problem. These are readily solvable. And so you can get the Slepian sequences by solving this eigenvalue problem. And the Slepian functions are then simply the discrete Fourier transform of these. The eigenvalues follow from the definition. What do these look like? Well, this is a 1,000 points with a time bandwidth of 5. This is the first 6 of these eigenfunctions. The first one looks like just like any ordinary data taper that you might use, like for example, a Hanning window. The second one has a single zero crossing. The third has 2 zero crossings, and so on as we go up. The eigenvalues are given there at the top. So the energy concentration of the 0th order one is, I don't know how many 9s that is, but a lot of 9s. It gets smaller as you go up. The next one is two 9s less until you get up to the 5th one where it's only got 5 9s of energy concentration. If you compute the Fourier transform squared of these things, you get these. These are the square of the Slepian functions. Again, this is a time bandwidth of 5 or a bandwidth of 5 1,000ths. Sorry, I'd use 10,000 here, so it's 5 10,000ths. You see that in the first case in the upper left, you've got what looks like a pretty standard window. As you go up, and you've got 130 dB of side lobe protection. As you go to higher and higher orders, you're getting less and less side lobe protection. So the third one at the upper right has 10 orders of magnitude instead of 13. And if you finally get to the 6th one, you've got 6 orders of magnitude. It's still pretty good, but you know, you don't get a free lunch in this world. So a simple recipe for computing a multi-taper estimate would be to choose the resolution bandwidth W. W is just R over N, where R is an integer like 3, 4, 5, somewhere in that range. You fix the upper limit to the number of tapers to be 2NW because the eigenvalues fall off exponentially above that value. You compute K raw spectra and average their absolute squares frequency by frequency. So you take the Slepian function nu nk, multiply by the data set xn, compute the discrete Fourier transform, and average over average the absolute square. The quantity b sub k is there just to make sure that you don't have bias in the outcome. Clearly, b sub k is 1 over root lambda k, so that is in fact giving you the spectrum. This is actually a decent estimator and it works reasonably well, but there are better ways to do it. And the better way to do it is adaptive weighting. So instead of putting that constant bk in there, we'll put dk, which appears here as the square, which is now frequency dependent. And so the spectrum is the sum of the absolute squares of the Fourier transforms of the windowed spectra times lambda k times dk squared, and then of course appropriately normalized. I won't go through the derivation here, but it turns out that the dk can be shown to be what the quantity in the middle equation. The denominator of this is a weighted quantity. The population value of the spectrum S multiplied by the eigenvalue. The right-hand term is the broadband bias. So this is the bias outside of minus WW, and it's bounded by the variance of the data times 1 minus lambda k. So if there is no broadband bias, and then this thing reduces to 1 over root lambda k, just as it did when you were doing just the blind estimate. If, however, the broadband bias sigma squared times 1 minus lambda k is large, this weight will get much, much smaller. One way to make this work better is to pre-whiten the data. This pre-whitening is the use of a time domain filter that reduces the spectral dynamic range. The simplest way to do this is to differentiate your data. A better way to do this is to simply fit an AR filter to it. This is nothing but the maximum entropy estimator. You're gonna take it out of the data and put it back in at the end, so it doesn't have any effect on your spectrum, but it does serve very well to reduce the dynamic range. This is something I routinely do when I'm computing a multi-taper estimate. The degrees of freedom then are this quantity nu of f, which is just 2 times the sum over the number of estimates k, bounded by 2nw, lambda k times dk squared of f. Pre-whitening is essential towards maximizing this. And finally, you can do a simple least squares application to the multi-taper estimator to estimate the amplitude of harmonic components, these things called mu hat. And the reason this works is that the shape of the spectrum is defined by the Slepian functions, and you can use those as basis functions to look for the amplitude. So the power in the line is the absolute value of mu hat of f squared. You can actually take the power in the line out of the spectrum and get a reshaped version of the baseline spectrum after removing a line. That's the quantity in the middle. And finally, you can devise an f-test for the presence of a spectral line component. A spectral line component has 2 degrees of freedom. The residual spectrum after removing that line has nu of f minus 2 degrees of freedom. And this quantity at the bottom is distributed, therefore, as Fisher's f with 2 and nu minus f minus 2 degrees of freedom. So you can therefore have an objective estimator for whether a line component is present or not. So as a first example, I'll show you length of day data. This is length of day data from 1962 through 2013. Of course, it goes to the present day but I don't have those more recent data. This is delta length of day in milliseconds on the y-axis and time in days on the x-axis. If I pre-whiten this with an autoregressive filter of about, I forget what I used, probably about 5 terms, you get something that looks like this. It looks like it has been whitened. It looks more like a white spectrum. It's a bit disturbing that it gets higher amplitude at the end than at the beginning. This is almost certainly instrumental. The ability to make these measurements has gotten way better in recent years than it was in the early 60s. If I compute a multi-taper spectrum of this data set using the adaptive weighting that I described earlier, you get this. This is the power in milliseconds squared per cycle per year on the y-axis and the log of frequency in cycles per year on the x-axis. So what you see is a red spectrum, at least above roughly 0.01 cycles per year, with superimposed on it peaks that look very square. That's characteristic of a multi-taper estimator, that peaks tend to look square, and that's because the spectral window of the multi-taper estimator is in fact nearly a perfect square. If I compute the degrees of freedom of that estimator, I get this. This was a time bandwidth of 4. I used 7 windows, therefore the maximum degrees of freedom is 14. And as you can see in the high power parts of the spectrum, you get very close to that. In some of the other parts of the spectrum, you do not. You get down as low as 10 or even 9. Obviously you can adjust the autoregressive filter order and improve on this if that becomes important. It's not in this case. What's going on? If I blow up a section, I don't know, for some reason it wouldn't let me advance the spectrum. If I blow up a small part of this spectrum between, in this case, minus 1.6 and minus 0.6 cycles per year, and you look closely at these peaks, you'll see that one of them, which is the one right in the
alert from calendar, MasterCard,
which is the one right in the middle, it actually looks very pointed as opposed to being square. It turns out that this is the fortnightly tides. There are two components of the fortnightly tide whose frequencies are very close together, too close together for me to resolve with this spectrum. And so the result is something that doesn't look square. If I perform an f-test on these data, the blue is the f statistic computed from the spectral estimator. The three horizontal lines are the quantiles of the F distribution at 3 nines, 4 nines, and 5 nines probability. And you can see that these peaks are quite significant. Now it's working again. And so if I reshape the spectrum, that is to say, I pull out the harmonic components from it, and I'll put the power at those harmonic components back in on the assumption that their bandwidth is 1 over the length of the data set. And those are the red pluses. I get this. I get rid of almost all of those line components. I do not get the fortnightly tide out of there because I can't resolve the 2 frequencies of it. And I'm missing some other things up there at the higher frequencies as well. The Chandler wobble is shown at the left. There's essentially no effect of the Chandler wobble. And so this is the spectrum after having removed the power in those. So I've shown you a univariate method of computing the power spectrum. You can just as easily compute the bivariate quantities like the coherence, or multivariate quantities like the transfer function with the multitaper estimator. You can also deal with irregular sampling, where the sample interval between the data is not 1, or if you like, array processing. And you can deal with the non-stationary processes, which I'll talk about next. I'll point this out. This is a paper I published in late 2019 where I extended the multitaper spectral estimator to time series that have missing data. So you can in fact compute a spectrum of time series that have missing values. There's MATLAB code for this available on the MathWorks website. This works. It doesn't work as well as, of course, as if you had all of the data, but there are times when this may be what you need. So I said at the beginning that a stationary process, the expected value of the Kramer or the increments process dz of f at distinct frequencies f1 and f2 is 0. That's not really quite right. It's actually the population spectrum s of f1 times a delta function times df1 df2. It's got a delta function discontinuity in it, which doesn't really matter for practical purposes. If the process is non-stationary, however, the expected value of this quantity becomes the Loewe spectrum, SL. In other words, if a process is stationary, distinct frequencies are uncorrelated in the spectrum. If it is non-stationary, that's not true. They are correlated. That is given by the Loewe spectrum, named for the French probabilist Michel Loewe. It is important, I think, important to note that if you force a non-stationary system at a given frequencies, that will result in the redistribution of power to other frequencies, and the correlation of the spectrum at the 2 frequencies will be high. This is inherently a nonlinear process, so non-stationary processes are inherently nonlinear. I'm going to look at geomagnetic data from Honolulu Observatory in 2001, 2002. And I'm going to use 2 quantities to look at these data, looking for non-stationary activity in them. The first of these is to compute a standardized spectrum, which I obtain by taking the standard multitaper spectrum and post-whitening it by fitting and removing a quadratic polynomial. So instead of having a red spectrum, it'll flatten it and become a horizontal spectrum. This has a known distribution, and I can use that known distribution to make statistical inferences about it. Instead of computing the Loewe spectrum directly, I will compute the coherence versus 2 frequencies. One is the ordinary frequency that we're used to in stationary processes. The other is an offset frequency about the ordinary frequency. And I will plot this quantity conditional on its true value being 0, meaning that there is no non-stationarity. So I'm going to transform this coherence, and I'll describe what that means in a minute and how that's being done. I should add that all of this work was originally started by David Thomson, who's been working on this topic for 25 years or more, and has shown that that this non-stationary is pervasive in, for example, seismic data, barometric pressure data, lots of terrestrial data. Well, this is just the standard multi-taper spectrum, averaged over 3 60-day sections, and I'll get to why I'm using 60 days in a minute. It has a time bandwidth of 5 and 9 spectra, so they're about 54 degrees of freedom. From top to bottom, these are the north H, the vertical Z, and the east D components. I'll point out a feature of this, which is that over 2,000 to 4,000 microhertz, and I'm going to be doing everything in terms of microhertz just because it gives you reasonable numbers instead of tiny little numbers. So over at the far right, you'll see that there is an enhanced amount of variability over 2,000 to 4,000 microhertz. That's the log of 3.3 to 3.6, or if you like, it's periods of 250 to 500 seconds. So there's enhanced variability in H and D. You don't see it in H and Z, not in D. What is this? Well, I'm going to assert, and I'll try to demonstrate, that this is in fact caused by the presence of solar normal modes in the spectrum, and I'll show you examples of this in a second. Just a little background. The sun, just like virtually every other body, oscillates, and this oscillation can be represented by quantum numbers n, which is the radial quantum number, the number of nodal points going from the surface of the sun to the center, by an azimuthal, I should say latitudinal quantum number L, and then a longitudinal quantum number M, which exists only because the sun is rotating and has a magnetic field. Each one of these modes is characterized by a central frequency and a Q. The ones I'm concerned with here are pressure modes, P, N, L, M. These are acoustic standing waves in the sun. They exist over about 250 to 5,100 microhertz, or if you like, periods from a little over an hour to a few minutes. These are excited by turbulence in the sun, and so their amplitudes are random. They exhibit Qs of several thousand. They therefore persist for a month or two. The reason I used a 60-day section in the previous spectrum, and I will use it going forward, is that is sort of the persistence time of them, and you would expect to see them over that. If you took a much longer time spectrum, you would tend to average them out. So what I did first is I took that power spectrum that I had before, and I'm going to fit a mixture model of a central and non-central chi-square distribution. And I'm going to do this over that 2,000 to 3,000 microhertz band where I saw that enhanced variability. These are for 3 separate 60-day sections over year days, 298 to 358, and so on. In the first case, I can't fit the non-central model. It just doesn't fit very well. I'll show you why in a second. So in each one of these plots, the solid line is a kernel density fit. So this is just an empirical PDF fit to the data. The dot dash line, which nearly matches with the kernel density fit, is this mixture model where there's a non-central and central chi-square distribution with a fraction epsilon of the amount of non-centrality present. The central part is shown as the dash line. The non-central part is the dotted line. And so for these last 2 sections, I get a non-central fraction of respectively 0.29 and 0.4. So 29% and 40% non-central contributions to these. And the fit is actually pretty decent. I said before that the first section didn't fit very well. These are the KP indices. That first index, which is the first interval at the left, has in fact 3 very, very high energy intervals, KP approaching 9, which is the max. I believe that first section is dominated by simply extreme solar variability. Solar cycle 23 actually ended in 2001. So this would be the last gasp of that particular cycle. The next 2 sections where I'm finding a reasonable fit of the non-central distribution are shown at the right, and they're much less active. So what I'm showing you here is a standardized spectrum at the bottom and an offset coherence at the top. the offset coherence has been transformed such that a value of 1, 2, 3, and 4 is 0.9, 0.99, 0.999, and 0.49s and greater probability of correlation. So these are, if you see red, it's pretty highly correlated. The spectrum at the bottom shows the probability of occurrence from the quantiles of the distribution of the standardized spectrum. And so you see two frequencies here where the spectrum is as high as 0.99 probability. The green lines are the known frequencies of solar normal modes, including the rotational splitting terms, which are the individual green lines. And so two of these occur with 0.99 probability at P35 and P42. The apparent Qs, which are determined by the resolution bandwidth of this estimator rather than by the modes themselves, if that's what they are 270 and 400 respectively. So these are very high Qs. Certainly in what we know of the magnetosphere, the Qs are of any features that the space physicists have found are 2 to 5. They're nowhere near this high. So I think what you're seeing there are normal modes. If you look at the top, the probability of, for example, the P42 is at the 4 nines level. And if you look up and down on there at the offset frequency, these things are correlated across frequency. Although interestingly enough, the two peaks that you see there are not correlated. If I take the offset coherence and now I integrate across ordinary frequency, I'm going to take the 811.5 P42 peak, I'm going to integrate across ordinary frequencies so that I just get coherence against offset frequency. The resolution of the offset coherence is the resolution bandwidth of the estimate on ordinary frequency, but it is the Rayleigh resolution, 1 over the length of the data set on the offset frequency. I get this. At the center frequency in the middle, you see the peak, and you see two sidebands, if you like. These are approximately 440 nanohertz away from the central peak. That is, in fact, what the rotational splitting ought to look like. The vertical dotted lines are, first of all, 0.5 cycles per day, and second of all, 1 cycle per day. Because the Earth is rotating, you would expect to see cyclostationarity at 1 cycle per day, because you're viewing the sun through a rotating reference. You don't see a lot of coherence there at that point, but you do see some at a half cycle per day, and there's a nonlinear process in the magnetosphere that can produce this. If I go higher in frequency now to 1310 to 1410 or 1320 to 1420, I now get another series of peaks. There's one here that's 5 nines in probability, has an apparent Q of 695, and you can see that these peaks across this band are highly coherent. Those red parts indicate that they're highly coherent and therefore highly non-stationary. And finally, if I go up to 3000 microhertz, which is in the band where I found 40% non-central, everything is coherent with everything. Look at that trapezoidal feature in the offset coherence between 3250 and 3350 roughly microhertz. All of these peaks are coherent with each other, and some of these peaks have probabilities as high as 5 nines. The red lines are the frequencies, the center frequencies of known normal modes. Obviously, if I put in all of the rotational splitting terms, this would just be a picket fence of red all the way around. And that's the end of that. Maxwell will now take questions and I'll attempt to answer them. If anyone wants further details on this, I have a set of lecture notes. I'd be happy to send them to anyone who wants them. Just send me an email at chave@hui.edu.
Yes, Alan, thank you very much for that. And yes, we are ready for questions. So please use the Q&A feature to type in your questions. So maybe just to kick off while people are sort of gathering their thoughts and typing in questions, can you were talking about these normal modes and the quantum numbers, yes, and the different sort of standing modes, and also the frequency. I have to admit that it's not entirely clear to me sort of what the process is, because I'm imagining sort of the sun, if you want, so oscillating as a whole, but for that the frequencies seem very high given the size of the sun and so on. So can you sort of say a bit what's happening there?
These are acoustic standing waves. There are several classes of normal modes. They can be measured optically, and they have been measured optically for the last 25 or 30 years with various satellites. Basically, you're doing a fit to the optics. Their scales can be very small. I mean, up at 5,000 microhertz, they're quite small, as you might imagine. If the quantum number L gets up to being hundreds, then that means there are hundreds of nodal points in latitude. But they're certainly very real. They are probably the best way to learn how the sun is operating, or how what the internal structure of the sun is. So therefore, they are a very hot topic. It's called helioseismology, to be direct.
Yeah, okay, but okay, so I think the thing I sort of didn't realize that these are at these, like, as you say, really high quantum numbers, so they're small scale features. I was more thinking, like, when you talk about normal modes of the Earth, you think about these sort of, whole Earth sort of oscillations, and of course, they are probably also there in the sun, but they occur.
Yes, there are certainly low frequency versions of these, and there are other classes of normal modes. There's something called the gravity modes, which have never actually been measured, but exist theoretically. These are sort of like internal waves in the ocean. They don't have a surface manifestation. They have an internal manifestation. The helioseismologists would love to actually measure gravity modes, because they have they're large, deep within the sun, and they would provide information about the structure of the sun that you can't get from acoustic modes.
Yeah, well, I suppose just like the standing modes or standing waves in the Earth, yes, where you kind of go deep into the core and can sort of get whole Earth properties.
That's exactly right. It's completely analogous to terrestrial normal modes. Still no questions?
Still no questions, at least. No, there's one. Okay.
You gonna read it, Max, or should I?
I can read it and then you sort of answer it. So if we have noise in the data, adaptive weighting is biased to noise. How do you solve this problem?
It actually isn't biased to noise. You will not use the part of a spectrum where that noise, if you like, the broadband bias is what I call it, is large. It'll basically downweight the spectrum. So it's not biased to noise, it's biased away from noise.
Okay, maybe while some people are thinking about more questions, maybe just because you were talking about things which I think are quite interesting, but are probably a bit different from what many of us think about every day. But of course, this whole multi-taper spectral estimation is part, for example, of BERP, right? I mean, that is one of the central.
No, BERP is a WOSA estimator, Welch overlap section averaging estimator, because in magnetotellurics, typically you have a long time series and your frequencies of interest are not of order 1 over the length of the time series. I do use a Slepian function in BERP as a data taper, because it is the best data taper out there. But that's as far as it goes.
Okay, so actually, so that then it sort of, that turns it into a question. Okay, because yes, I remember reading in the documentation, in the papers, you're talking about the Slepian functions and the time bandwidth factor that you specify when you do your BERP processing, but then all that just, you basically select one of those Slepian function as a taper and do a standard Welch estimate. Is that,
That's correct. That's I think every other robust estimator that's out there basically works in the same way. And it works because your frequencies of interest are not typically 1 over the length of the data set that you have. In the rest of geophysics, very often it is the case. And so when I do any spectral analysis, I either use a WOSA estimator if that's appropriate, or I use Multitaper. I don't do anything else.
yes, and of course, I mean, definitely the VOSA things, they are readily implemented in basically anything one would use today, MATLAB, yes. Python, whatnot. They're not particularly difficult. I'm not sure about the Multitaper, whether they're canned version or you have to roll your own.
I have provided, well, first of all, MATLAB, which is what I use exclusively, has a built-in function for it. I have uploaded to the MathWorks website a Multitaper estimator that includes the F-test and the harmonic, the reshaping of the spectrum that isn't in the MathWorks version of it. So it's publicly available. There's Fortran code out there written by Herman Prieto some years ago. I suspect that there's Python code out there as well.
Yeah, which is sort of definitely a good thing. And I guess there's no excuse anymore, or well, there hasn't been an excuse for a while already not to use one of those two methods.
I'd agree with that.
Okay, I mean, still, there haven't others. Okay, another question has come up. I think if the noise is coherent with data, you overweight it with adaptive weighting. That might need some clarification, or I don't know, is it clear to you?
I'm not sure what that means. What I'm dealing with here is not noise in the conventional sense, it's bias. In a spectral estimator, bias is where high power parts of the spectrum leak into low power parts of the spectrum and obscure it. Obscure features. That example I showed you of the, I'll bring it back up. This example here, where you have the periodogram at the top and the multitaper estimator at the bottom. The difference between these two is bias. It's caused by spectral leakage from high power parts of the spectrum in the periodogram into low power parts, and it's completely obscuring your features. So this is what I call broadband bias. It's bias outside of the band minus WW that you've chosen. It's not necessarily has anything to do with coherent noise. It's simply that bias that is inherent to any spectral estimator. You can't beat it. I should have added here when I put this thing up that our colleagues in space physics to this day continue to use frequently the periodogram estimator. You can pick up any issue of JGR space physics, and there it is. They've used the periodogram estimator. Therefore, they think that all of the spectra that they get from space physics data are featureless and have just power law behavior. It's terrible, absolutely terrible that they're doing this. Not all of them do, but a lot of them do.
Yeah, and I think maybe just to sort of as a comment from my side, yeah. So what you're talking about is not necessarily distinguishing like an MT. We have our wanted signal, and then we have some noise on top that comes from, I don't know, some cow fence or something. But it's more about getting actual sort of the correct spectrum that you can then work with and even identify, for example, the lines from, let's say, the cow fence or something. Because I mean, if you would do a periodogram on that, you would probably get something similar to what you show here in the black line, just
right.
Some random wiggles, and you can't even see that there is maybe, I don't know, an electric fence power source somewhere that
if it's strong enough, you probably would, but it's not terribly informative. I mean, the difference between these two spectra is 8 orders of magnitude at the highest frequencies. That's quite a lot.
Okay. Thank you very much, Alan. It seems, oh no, whenever I seem to think that all the questions have been asked, there's another one. So you mentioned the method could be useful to fill gap in time series data set. How does the estimated data in the gap correlated with the real data? If there was real data in the gap, okay, I guess, yeah, if there,
yeah, that would be pertaining to the GGI article that I showed. The top. You don't actually, with this method, you simply compute a Slepian function that exists only where there are data. You aren't creating data that fill the gap. You're simply using what there is with a Slepian function that accommodates the gaps in the data. You obviously are not going to do as well as you would have if you had all of the data, but it does work under fairly general circumstances. But it's not an interpolation method. There are lots of those out there. This is actually a way of accommodating the gap in the data.
Okay, so let's see whether somebody will be finished with typing right now. So otherwise, thank you very much, Alan. That was very interesting. Thank you everybody for attending. And yeah, just a quick reminder. So next week, Joel Jansen, natural source EM methods for mineral exploration. So if you have an interest in sort of applications of, well, MT and I suppose other EM methods, then tune back in next week. I will be leading this Eminar next week as well. And then I think in 2 weeks, Alan Jones will be back. So again, thanks, Alan, and have a good day, everybody.
Thank you.